So we left off last time with introducing this example problem, and I said, well, let's work this example on the next video. It'd be a long video if we had tried to work it in the previous one. Now, if you're just watching the example problems, that's okay. You're welcome to do that. You're missing a lot of detail when you do, but anyway, if you're just watching the example problems, you're welcome to go ahead and copy this down as I'm kind of talking about some basic stuff here. So again, this is a frame. We have a force applied not at an endpoint of this member. We also have pins right here not at the endpoint of these two members. So these member A, B, C and member C, D, E are going to be multi-force members. I can't treat those as trusses. Now, or I can't treat those the way I would truss members. Now, member BD here, though, that one ends up being a little bit different. We're going to talk about that. But we'll see, we're not going to treat it differently right off. We're going to treat them all the same. When I'm dealing with a frame or a machine, I need to be prepared to treat each pin as having an unknown vertical and horizontal component, an unknown X and Y component. So what I can do is I can take this thing apart, and through the magic of pre-recorded or pre-done notes here, I can show you. You can draw free body diagrams of each individual member. You can take each one apart. So if I take member A, B, C apart here, I can do that. I've got a pin at A, a pin at B, and a pin at C, and this this known applied 5 kilonewton force. So I can draw this free body diagram of A, B, and C, where I've got pin forces, horizontal and vertical, X and Y unknowns, at A, B, and C. Now, notice my preference is to go through and systematically draw each pin force in the positive direction on the first free body diagram where I draw it. The second free body diagram I draw it, I tend to draw the negative of it. Because if I put these two together, these equal and opposite forces will cancel out. They're only exposed when I take this thing apart. So if I draw free body diagrams of each side of this pin, I've got equal and opposite forces that when I put them together, they will cancel out. So you have to be very systematic about whatever direction they are on one free body diagram, they're going to end up being the opposite on the other. So you want to have some way of systematically keeping track of your signs. And notice over here we draw CDE. I've got a roller down here at E, so we're going to apply normal force from the horizontal surface, a vertical normal force there. I've taken apart point D. If I draw this one first, this is the first time I've drawn these, so I draw both these positive. This is now the second time I've drawn C, so I would draw these negative because these need to be equal and opposite. And then again, if I've drawn D and B both initially, then when I draw their counterpart, they need to be opposite. All right, so I just wanted to show you can draw all three of these free body diagrams, plus you can draw, and we're going to draw a free body diagram of the whole thing, because a lot of times you can find at least some of the reactions, if not all of them, right off. And those will be helpful then, because once I know the reactions, then those are fewer unknowns on these other free body diagrams. But I wanted to show you, you've got three free body diagrams here, 3 equations for each free body diagram. That's 9 equations so far, plus a free body diagram of the whole structure. That's 3 more. I'm up to 12 equations. There's a lot of unknowns here, but I don't think there's more than 12 unknowns here. So all that to say, we will be able to solve this thing. We just need to throw enough math at it, and that's kind of sometimes what we do as engineers, is just keep throwing math at it until we find a solution. We just got to do it in the right systematic way. So let's work through this, shall we? Okay, so what I'm going to do is I'm going to draw a free body diagram of the whole structure. It can be very simple. This A frame, I've got AY and AX over here. I've got E over there, and I've got this 5 kilonewton force that is being applied 3 meters from the bottom, and then it is a 6 meter span across here. And I think that's all I need to solve this. So I'm going to pause and write out the answers here Actually, no, I'm not even going to pause. I'm going to write out the answers. Go ahead and pause if you need to practice finding reactions. You should be able to find these pretty quickly. So go ahead and pause if you want to find the reactions. I'm going to go ahead and write them out here. I'll go ahead and pause and write them down. Okay. You need to be very practiced at this point trying to find reactions. If you need help on that, please get it. And please stop by, ask me if you need help. But you need to be able to solve this very quickly. That's chapter 5 material, the early part of chapter 5. So now we know the reactions. What are we looking for? We're looking for the forces at point D. So that means I'm going to need to be able to... D is attached to member CDE here or member BD. There's no known forces on BD, so it doesn't do me much good to draw a free body diagram BD right now. But there is now a known force right here at point E. I've just found the reaction at point E. So I can draw a free body diagram of member CDE here and possibly find some forces there. Okay, so if I do that, so if I draw a free body diagram now of CDE, so I'm going to draw E here. I'm going to draw D. I've got point D. It's a pin. So I've got DX and DY. Now, and then I'm going to draw point C. Now, this is the first time I'm drawing it. I know I showed you some diagrams earlier that I had CX and CY in the opposite direction here, but just systematically, this is the first time I'm drawing them here. So I'm going to go ahead and draw them in the positive direction. Distances here from C to D is 2 meters, from D to E is 2 meters vertically. So 2 meters vertically there, 2 meters down to E vertically, and then distances here are 1.5 meters horizontally from C to D and 1.5 meters horizontally from D to E. We do know from up here that E is equal to 2.5 kilonewtons. And this is the same side of CDE that I'm drawing here, so I can leave the force in the same direction. It is 2.5 kilonewtons going up, pushing on this point right here going up. Okay, so what I can do then is I can say, well, sum of forces in the x direction equals 0. That's going to be, I've got CX and DX. Okay, so that's one equation, two unknowns. Can't solve that one. Sum of forces in the y direction, that's also equal to 0. I've got CY and DY, and then I've got plus the value for E. Okay, now I've got two equations with 4 unknowns. Not so good so far. What I can do, though, is I can say, well, what about if I take the sum of moments about some point? I could take the sum of moments about any. I've got 3 points here I could take the moments about. Man, which one? Well, there's not a right or wrong one. But remember, we're looking for horizontal and vertical components of point D. So, truth be told, I really am not so concerned about what are the forces at point C. All I really need to know is I need to know the point D here. So if I take my sum of moments about point C, these unknowns here both pass through point C, so they cause no moment. I'm going to get an equation with just these two unknowns in it and this one known quantity. So if I look at point C, dy is causing a counterclockwise or a positive dy at a distance of 1.5 meters. That's the moment caused by dy. Dx also in a counterclockwise fashion, so also positive dx, and it is a distance of 2 meters. And then I've got E also causing a counterclockwise rotation as it's drawn, so plus E, and that is a distance of 3 meters. Okay, so 3 equations, 4 unknowns, because I do know E, so I can plug E in there. here and here, but I still have 4 unknowns: dx, dy, cx, cy. So I knew I could only write 4 equations here with 4 unknowns. I knew I couldn't solve it right off. But what I can do then is I can do, what else can I do then? Well, I can do a couple things. One thing I might do, now maybe this isn't what I would do if I was actually solving this. This is not the fastest way to solve it, but just to show you. Let's draw a free body diagram of ABC. Let's draw a free body diagram of ABC. All right, so if I draw a member ABC, I've got pins down here, A, Y, and AX. Those are known, by the way. Those are reactions I found earlier. I've got a pin right here at B, so I'm going to draw BX and BY, both positive. I've got 5 kilonewtons there, and then again I've drawn CX and CY positive here, so over here I need to draw the opposite of those. I'm going to draw CY and CX in the negative direction. Now remember, we found both AX and AY to have negative values, so if you would like, I've drawn them positive here. If you'd prefer, you can draw them as we found them. We found them, this AY to be minus 2.5 kilonewtons. You can draw it in the negative A direction. I apologize. I should have drawn it that way initially if that's what I wanted to do. And AX is in the negative direction, 5 kilonewtons. We found those earlier. So you can draw them as AX, AY and plug in negative values in your equations. Or you can draw them in their negative directions, which is what we've found them to be. Either way is perfectly okay. It's your free body diagram. It's there to help you. Draw it in such a way that it is helpful for you. This is 2 meters. This is 1 meter up to the 5 kilonewton force, and 1 more meter up to the top. As we discussed earlier, it's 1.5 meters out here to point B, and then 1.5 meters out to point C. I don't have room to write that there. I'll put it on the next page or something. Yeah, we'll just draw it in here. 1.5 meters. This is a terribly drawn free body diagram. I apologize. I should just redo it. Okay, so what can we do here? Well, what do we need? Right? I could go ahead and just blindly start writing equations. I could write sum of forces in the X, sum of forces in the Y, and be good. But what do we actually need here? Well, notice I've got 3 equations. I've got 3 equations up here and 4 unknowns. And CX and CY are unknowns up here. I don't necessarily need to know BX and BY. But what I could do is I could do something like I could take the sum of moments about point B, set that equal to 0. It's going to be a long equation. But if I take my sum of moments about point B here, well, BX and BY both pass to this point, so they cause no moment. I have this, if I just start down here and work my way up. So this 2.5 kilonewtons is causing a counterclockwise rotation, so it's 2.5 kilonewtons, that's AY. And that's a distance of 1.5 meters from point B. This is causing a negative or clockwise motion. This is minus 5 kilonewtons, that's AX, minus 5 kilonewtons, and it is acting a distance of 2 meters from point B. On the second line now, I've got more terms to add. So point B is what we're taking our moment about. I've got this 5 kilonewton force here. This load here is applying a moment about point B. It is negative, is clockwise. So minus 5 kilonewtons. Again, it has nothing to do whether it's positive or negative X. It's in the clockwise direction about point B. 5 kilonewtons at a distance of 1 meter. And then as I've drawn it here, CX is trying to cause a CY. CY is trying to cause a I guess CY is trying to cause a clockwise rotation about point B. CY is trying to cause a clockwise rotation about point B. So that's minus CY, and that is a distance of 1.5 meters. And then CX is up here. As I've drawn it here, it's trying to cause a counterclockwise rotation. So that is plus CX at 2 meters. Note what we've got now. I have 1, 2, 3, 4 equations with 4 unknowns. That is solvable. I'm going to pause here and let you do that algebra, and let's talk about it. Okay, let's finish up here. Did some algebra, made a mistake a little bit later, but I caught it pretty easily. All right, so from this free body diagram, I'm going to solve this equation. Rewriting this moment about B, I find 2 times Cx, times meter if you will, minus 1.5 Cy times meter, is equal to 11.25 kilonewton meters, and the meters are in each term, so they go away. Some of you guys have noticed, don't carry your units through your calculations. That will come back to haunt you in later engineering courses, I can assure you. You can kind of get by without it in statics, but it's a good habit to be in. All right, so that gives me a 4th equation, right? Take this equation, couple it with these 3 equations. That gives me a 4th equation with these other 3. So if I take this one and solve for Cx, because I don't need it, I'm going to solve around it. I'm going to solve for Cx and this one for Cy. That's what I've done here. So I've got an equation here that we just solved down right here, and I solve the free body diagram from C, D, E. I solve for Cx and Cy. Cx being minus dx, Cy being minus dy. I take these and I plug them into this equation, and that's what I get here. So minus 2 times dx plus, well, and this is minus 1.5 times minus dy and times minus e. So it's plus 1.5 dy plus 1.5 e. So because I'm taking minus 5 times both of these, that's right here. And that's going to equal this 11.25. I managed to accidentally put a negative sign on it earlier, but I corrected that. So that's equal to 11.25. All right? So that's one equation. Now, I've got another equation up here. This one, some moments about C from up above, that also puts dx and dy in the same equation. So now I've simplified down to one equation with dx and dy in it. I've got a second equation with dx and dy in it here. So I've moved this down here, solved it. Notice I've lined these up. I've got minus 2dx plus 2dx here. I've got 1.5 dy and plus 1.5 dy here. So basically I've just taken these two equations and added them together, rearranged them. The dx's go away. You add these 1.5 dy's, that gives you 3 dy. I'm going to take this 1.5e, move it over here, and put it over here. So 1.5 and 3 combined to be a minus 4.5e. Add to it this guy, this 11.25. So again, I've combined these two equations into one. I've got 3 dy is equal to minus 4.5e plus 11.25. Remember, we've got a value for e. E is 2.5 kilonewtons. So minus 4.5 times 2.5 gives me a negative 11.25. Add to it, positive 11.25. This is 0. 3 dy is 0, dy is 0. Maybe that's Steve, does that make sense? Well, maybe. But with the value for dy now, either one of these equations up here, knowing the value for e, I can solve for dx. And these are my answers. This is what the problem was asking for. The vertical and horizontal components of the pin force at point D. Now again, does this make sense? Does it make sense that this would be 0? There's a few ways we can check that. Here's one. If I draw the free body diagram of B, again, remember, on our other body diagrams, I've drawn D pin force as positive, and here I've drawn B pin forces as positive. So I've drawn both of them positive once. I'm going to draw them both negative now because I'm looking at the other side of that pin. So when I put these together, they'll cancel out with the ones I've already drawn. Notice what happens if I take the sum of moments about point B from this free body diagram. Sum of moments about point B, the only one causing a moment about point B is the dy right here. And so if I say, well, sum of moments about point B is 0, I've got dy causing a clockwise moment at a distance of 3 meters, and that's equal to 0, so that means dy is 0. The other way to look at it is BD is a two-force member. How do I know that? I can go all the way back to the original diagram. Notice that member BD here only has forces applied at the endpoints. There's no force hanging in the middle in here. There's nothing else applied in the middle. He's just pinned on both ends. When I've got a member within a whole frame that I see that it's just a single linkage member and there's nothing else applied to it, I can treat it as a two-force member. I can treat that one member as a two-force member. And what I wanted you to see is you can prove it to yourself mathematically easy enough. You could just draw a free body diagram of that guy, take the sum moments about one end, notice that y component or the perpendicular component is going to cause 0 moment because it's the only one causing a moment and the moment's 0. So this guy, all the force, because it's a two-force member, all the force is acting in the middle of it. So at any rate, right? So as I've drawn it here, it actually ends up being in tension. Right? I've drawn it in compression, and we found earlier that it was actually a negative value, so it's actually the opposite of this. So it's actually in tension at 3.75 kilonewtons. All right, that is a long video, but that's okay because the other one was short. I'm going to stop here.